So welcome to the third session of LOPSTR. It's my pleasure to chair it. And we will first start with a talk by Jurjo Rivas, who's going to talk about a rule-based approach for designing and composing abstract domains.
Okay, can you? Yes, great. Thank you very much. This is a joint work with José Morales, Pedro López, and Manuel Hermenegildo. Analyzing and verifying properties of the programs, it's a crucial part in the software development cycle, and abstract interpretation allows us to do so by constructing sound program analysis tools, which is great, but it gets some cost because due to undecipherability, we always are losing some precision, and eventually we'll need to define new analysis or to combine the others that we already have to prove arbitrary properties. Moreover, the generation of the definition or implementation of new domains, it's costly and it's not easy, and it usually requires a deep knowledge of the framework in which we are defining our new abstract domain, which is an extra problem that we have to face when we try to use abstract interpretation, right? Okay, so for the rest of this talk, we are going to stay in the Horn clauses and logic programming world. So programs are going to have this form, like we have the head, the literals, but we are going to use the prolog syntax instead of the Horn clauses syntax, okay? And a very fast pitch of what abstract interpretation is. Okay, abstract interpretation, it's a technique that allows us to over-approximate the semantics of a program by using an abstract domain. That domain, it's simpler than the concrete domain, that it's the original program, and under some conditions we have the guarantee of the analysis terminating, which is great, and that we are going to obtain a safe approximation of the concrete semantics of the program being analyzed. In this work, we are focusing in the top-down algorithm that was first used in MA3 and MAs and was mature in Play. This algorithm, I'm going to explain this figure right now. It's separated into two parts. First part is the tree, this T alpha, that it's an abstract domain of the analysis graph, and it captures the path. This path is an infinite object that it's giving us an approximation of the set of maximal entries of the concrete semantics. So, for example, I don't know if you can see this program. It's a simple prolog program that is computing the parity of a list of zeros and ones. So the abstraction of the maximal entries of this program here, it's this graph that we have in the middle. Forget about the nodes. Now we are going to see what it means. But this shape, it's the abstraction of the maximal entries of the concrete semantics of this program here. And the nodes are the data. This is the abstract domain that we are implementing in this example that is given by this very simple lattice. We have a top element, this B representing the bit. It can be 1 or 0, zeta 0 or 1, and bottom that. So this is the framework in which we are working, and we are going to focus in this D alpha, that is the abstract domain. Okay. Now, when we want to implement that D sub alpha, that abstract domain, we usually need to define a number of lattice operations that are the usual order. We have the join, you have the mid, we have this nabla, that is the widening operator, which is optional, which is the lattice related operations, but we also need to implement a number of operations over the abstract substitutions that are at least these 5 operations. You can have more, making it more complex, but you usually have this. I'm going to go pretty fast over them, but we have the abstract projection that, given this abstract substitution, we restrict the lambda to the set of variables Bs. We have this abstract extent that it propagates the success substitution, this lambda S, to the lambda call, the call that it performing the abstract call, that it unifies the literal call A lambda with the head of a clause K defining a predicate A. the proceed that makes a dual operation of the abstract call, and generalize that it's the join, the least upper bound of all the abstract substitution that we have at that point. This framework is, as I said, more focusing the logic programming or constraint home clauses, but it's the same for the imperative world. We only have to change a little bit some concepts that are equivalent. Okay, so now our objectives here are to be able to design a prototype abstract domains and their combination or composition rapidly, and we are going to try to do so by reducing the number of abstract operations that we have to implement, and also trying to make as easy as possible to reuse all the abstract domains that we already have, because it's a work that we already have done, and it will be easy, great not to have to do everything again. So what we propose is a language of rewriting rules to try to meet these objectives. So this is the syntax of the rules that we are going to use. Let us consider this this number of set of properties, L and C1 to CR, and we have this syntax for and on or rules. There are the two kind of rules that we are going to use. These L elements, we call them the left side of the rule. They belong to this the first L set. We have all these Ds. Each of them belong to one of these Cs, but not all the C sets need to have a guard. And we can have several Ds for only one of these Cs. Okay, as I said, we call them the guards. Then we have this right side of the rule. They also belong to the first set, the L set. And notice we have this label that allows us to know which rule it's been applied over which set of properties. And well, notice the rewriting that we are performing is destructive. So once we have matched the elements in the left side of our store, and if the cards are holding true, the left side is removed and we replace them by the right part, the right elements. Okay, now I'm going to talk a little bit more about important. From now on, these sets of properties are going to be the lattices of a number of different abstract domains that we are going to work over for combining or even defining. And also, when we talk about the store, we refer to it to the lattice that it's going to be rewriting at that moment, and all the other sets or lattices are going to be what we call the context. Okay. Now consider these sets. We have this store with these less or equal properties. We have this context that it's a polyhedron, a number of constraints, and we have this simple set of free rules. Okay, now the way we are going to proceed, it's very easy for the rules. First we select an applicable rule. This corresponds to this part of our algorithm. After that, the application of the rule will give us an element to remove, in this case this one, and an element that we have to add, this one. So after that, we do that, and then we update the stores, removing one, adding the other, and we can keep doing the same thing recursively. So the next step, what we do have is applying this rule. So we remove this element and add this new element. Okay, we keep doing it. So now it's this old element which is removed, and we add this here. And we will do it until no more rules can be applied, in which case this function applicable rule will fail, will return false, and then we get the rewriting store. This is the typical way of doing of rewriting a store with rules, and we can do it over a number of stores. In that case, we have to apply a fixed point over the number of stores that can be rewritten given by this set of sets of rules. Okay, now the OR semantics are slightly different because this time we are not rewriting over a single store given a number of rules, but we have two stores, store 1, store 2, and we have these rules. Notice this semicolon that maybe it's a little bit tiny, but what we are going to do this is one of these elements we are going to seek them in one store. The other one we are going to seek for them in the other store. But now, where are we going to rewrite? We need to create a new store over which we are going to rewrite. So let's see. This is a simple algorithm. We are in this situation which we have taken two stores because we can have any number of them. So we apply the rewriting over the pair. We choose an applicable rule. In this case is this one because we have these two elements. They have the same left value, and we know that y is bigger than 3 because of the context. So we enter here, we apply the OR rule, we select a rule, and now we apply the rule and update the store. We create a new store, the rewritten store. We remove the elements and add this right side to the store that we're rewriting. Okay. Now the way of proceed is the same. We remove here, we add here. Okay, we keep doing it recursively as before until no more rules can be applied. But in this case, there are several options. We can not keep applying rules because we have exhausted both stores. We have two empty stores, so I cannot do anything more. Or because I kept with two stores in which no rule can be applied. This is the case. So we check. Okay, they are the same. No, they are different. So we have this problem. Now what we are going to do is we compute the intersection of that two stores, because these rules are intended to capture the least upper bound. So when I have two abstractions, if two elements are the same, they are the least upper bound of two elements that are the same element, so I can keep that. So in this case the intersection is empty. Okay, I get the difference, that it's the union, because the intersection was empty. And now what I need is a function that, given a number of elements of an abstract substitution, returns me the top information of all that elements. In that case, it's just, okay, zeta is at top because I don't know anything about that element. Okay, we do it, then our rewriting store, it's going to be all the elements that I have rewritten, the intersection that is empty in that case, and the elements that we cannot know anything, so we send to the top of the lattice. Okay, we did that, and then, well, we only have one store left, and we finish the algorithm. Okay, these rules that we have seen can be used to define the fixed point operations that we have seen a couple of slides before, to define them as follows. Now I forgot to put it, but our lambda, it's going to be a tuple of m lambdas, each of them an abstract substitution. So in the case of the projection, it's simple. I only have to project in each of that substitution. In the case of the extent, what we are going to do is apply the unfixed point over the extension of each of them. Okay, the thing is, as I said before, what we don't want to do is to have to define all these operations. So what we do is the following. For the domains that we already have the operation, the abstract extent, we use it because it exists. If it doesn't exist, then what we are going to do is we need to have a set of rules for that domain that it's capturing that behavior, and we have a number of generalizations of the abstract extent to use in that case. So we would do that and apply the and fixed point, and we get the extent. The same thing happens with the abstract call and the abstract proceed. Okay, and the things are a little bit different in the abstract generalize, because in that case we have to decide what are we doing. If we are only combining domains, or we are using this system to define a new domain. When we are combining, that it's that case at the bottom, the abstract generalize does exist for all the domains, because our domains that are already defined. So we use it, we apply for each of these domains the generalize, and then we compute the and fixed point to make them share all the information, all the possible information. If not, we are going to have this case in which we have a number of domains for who we know the abstract generalize, and others for which we don't. For that we don't know, what we do is to apply the order writing, and then we also do the fixed point for the result. Okay, now I'm going to do a fast demo, and we are going to consider this property here, inf xa, that tells us that for all the elements in x, that it's a list, a is lower or equal than them. So if we think about how we can implement an abstraction for this property, we could think about, okay, if I know that x is an empty list, I can set this inf to infinite, because I have an empty list, everything holds in an empty space. So okay, if not, if my list is this way, and I know the inf of t, I have two cases. If it's greater or equal, it's lower or equal. So here we have to define this property, what we have is a number of different properties. We have some shape properties. We have some shape properties, but we also have numerical properties, and they are relational, so they are not trivial at all. So here we have that we know that the depth k abstract domain they deal with these shape properties. Polyhedra can handle the numerical properties. So our idea is going to be, okay, let's try to combine this depth domain, this polyhedra, and give some extra info to generate a new abstraction. So I'm going to be very fast. So we have this number of rules. I'm going to... Okay, now I'm going to this. Okay, so these rules that are a little bit ugly, but for example, here we are getting that if depth k knows that L is an empty list, then I can abstract L to this inf. These three rules, they are abstracting the greater lower bound. So here, for example, if I have two inf elements in my substitution, and I get that x is smaller or equal than y, I keep the smaller. This one here are the rules related to the list constructor, so help us to know what to do depending the shape that depth k has inferred about our list. And here at the bottom we have these list upper bound related rules that are abstracting things like, okay, if I have in one store this element, in other store this other one, and then I know that the negation of depth k of this one being empty holds, then I keep this. Okay, and what I just run, we can use it to... Okay, it doesn't want to work. Okay, I just run this, and this is an analysis that we obtain of using this set of rules over this partition. Okay, this partition predicate. This is the normalized version of partition, that what it does is, given a list, given a pivot, we get all the elements greater than x go to L2, and the others go to L1, and our set of rules are able to, at entry we don't know anything, so everything is at top, but at exit we get that for all elements in L2, x is lower or equal than that element, that it's the property that we would like to prove. And okay, we've used this same technique to define this inf. We also did the dual, that it's pretty straightforward once you have one, that is to get the sub. So in this same partition predicate, we get that here, that for all the elements in L1, X is bigger or equal than it. We also use it to get some multiset properties, and we are able to abstract that the addition of the elements in L2 and the elements in L1 are actually all the elements in L, so it's a permutation. And these rule generate domains are also being used to be able to prove shortness properties for a Q-sort algorithm, because we can combine the different information that we're getting from them to get the shortness. Okay, and now I'm going to conclude. Okay, this approach has some, we consider some benefits. One of them is it's pretty simple. The writing systems are very expressive, and it helps us to script and improve abstract domain given some rules in a very declarative way. However, there are some inherent challenges when we are using rewriting. Especially, we have to ensure the convergence, determination, and the correctness, because we are using them to define an abstract domain, and things can be a little bit problematic. And in our future lines of work, we are working in improving the efficiency. Right now, we have a prototype that it's doing a very silly way of applying rule, that checking without a lot of heuristics, and move beyond the prototype and try to do the same things with domains that are already implemented, and be able to compare well the precision gain or loss that we could have. And I think that's all. Thank you very much.
Thank you. Any questions?
Okay, thank you for the nice talk. And so in this quicksort example, yes, you want to analyze sortedness.
Yes.
And for analyzing sortedness, you also analyze with respect to this inf and sup,
Yes.
domains.
Yes.
How do you come up with this intuition that you want these
Okay.
additional domains?
Okay,
So can you automatically infer the new domains, inf and sup, from
the quicksort, like?
the goal of proving or analyzing with respect to sortedness?
I don't think so. In that case, was because we were playing around the idea of getting more information, combining domains, and we found that, for example, in the example, we could need a number of small properties that all together will give another bigger, and that's why we started doing this. But the idea of automatically detecting which property you concretely need and then generating the domain, it's not. It would be great, obviously, but it's not what we are doing. We know that, okay, I need in partition, I need this property, so I have this domain, this, and then I mix them using the rules. Okay, thank you very much.
Yeah, hi, thanks. I was just wondering whether the classical ways of combining domains are usually, say, product domain or
Yes.
a reduced product domain, which is more can be more precise than the product, which is just the sum of the
Yes.
combined precision of the individual domains. Do your constructions correspond in some way to product or reduced product, or are they something else?
Technically, what we have is a number of direct product, and then the rules are acting as the composition predicate that should be reducing it. But
Is that the AND rules, or?
yes, the AND rules.
Okay.
They should be acting as the composition predicate that, in that perfect case, will get the reduced product.
Okay. And the OR rules, are they also?
The OR rules are only for the domains that we don't know, we don't have anything, and we want to generate the least upper bound with them, or the widenings.
Uh-huh, okay.
Thank you very much.
More questions? Maybe I missed it, but it's a naive question. How do you? Where does the rule come? Where do the rules come from?
Oh, the rules are given by the user. The idea is that the user, instead of having to define all these operations, can give a set of rules and give adding or removing rules until it gets the abstraction that he desired.
Okay. So I was asking because in your demo, the set of rules look so easy to build.
Yes, well, it's an example that I was been working to see how are the rules, but at the end it was thinking about how do you want to behave the abstraction and keep writing rules, and the idea is to make it as easy as possible. Well, thank you.
Other questions? Okay, so let's send the speaker again.